So machine learning seems to be the biggest buzz out there right now. So what's the magic? The first thing we need to learn about this is that we need to understand the classification of machine learning. Here I have a really simplified way of looking at things. On the biggest circle outside, we have this general way of doing work that we are all used to. And within it, there's this machine learning way of doing things. And within that, there's a deep learning aspect to this. So what does that mean? With a grand engineering fashion, we always make tables to describe things. So here I have a very simplified table where you can see that for the regular way is just point observation, and it's deterministic. There's no database involved, and there is defined features. For a machine learning way of doing things, the style is statistical. It's not deterministic. And we do involve database because you want to learn something, you have to learn from experience, of course. And in the machine learning category, we have predefined features. And that differentiates between machine learning and deep learning. In deep learning, it's all the same, except there's no predefined features. So the natural question would be, so what are features? Well, I put an example that people are a little more familiar with. So in Variation Designer, if you want to model a probability density function, you have to have attributes. So features are essentially attributes that differentiate between one thing over another. So for people, it could be your hair color, how tall you are, your gender. Those are features. So in this case, the feature would be PVT corners, the algorithm necessary to define the device under evaluation, and all the random variables of the devices. So keep that in mind. Features are stuff that's important to a particular problem. Now, what is the flow of how to do this work? Well, it turns out machine learning is an iterative process. So you have a decision algorithm to begin with, and that decision-making algorithm will create a suggestions by the modeling. And the answer from the model may or may not be correct, so you have to verify that. And once that verification is done, the data is included back into the database. So that's where the learning takes place, and the retraining takes place. And then the cycle starts over and over again. So at some point, the hope is that all these iterative cycles will make the model prediction pretty accurate. So next time when a new case comes in, the prediction will be very good. So the concept is pretty simple. I will talk about how to exactly do it in the next few slides. So one thing that I like to emphasize is that when people talk about machine learning, most of people think that it's neural network related. But it turns out it doesn't necessarily need to be modeled by neural network. It could be modeled by a closed form equation, or it could be modeled by a neural network. So here I'm making a differentiation. In this example is you could do a kernel density estimation, or you can do a deep learning neural network methodology. They are both machine learning. But in this particular talk, I want to talk a little more about the neural network because that seems to be a topic of interest by a lot of people. And to make the process a little easier, I thought I'd give a really simple example of how machine learning works in a neural network environment. So here I have a very simple chart of database. And in this particular problem, I'm trying to answer is this person an Olympian or not? So we all know Michael Phelps is an Olympian. And we all know, me, Ting Ku, I am not an Olympian. And I also put Z there and Missy Franklin. So over here, essentially, what we have is a whole bunch of people who we know for sure is an Olympian or not. And this is a database that we want to use to train the process. Now, the training happens by looking at the attributes or the features that I mentioned before. Over here, we list out the features like height, reach, how big is the wingspan, body mass index, the number of year trained, and gender. So we all know the most important feature is probably the number of year trained. If you don't train, you're not going to be very good. But would the machine learn about that? That's the interesting point. And so a typical neural network mechanism goes like this. You take the features and you apply a particular weight, which we don't know yet. And you put the data into an activation function, and it will answer the question, Olympian or non-Olympian. What happened is that because in the previous data, we have a known answer, then you can play with this weight. Eventually, at some point, you find a magical weight function to successfully answer the question from the known database, right? So think of a kind of a guessing. You keep guessing the weight until you get the right answer for the known database. And once you do that, we get to predict somebody else, like Amit, to see if he's an Olympian or not. And hopefully the model is accurate, then you can predict that he is.
What's the answer?
So to answer that question, we need to know your height, your reach, your BMI, and the year trained. So please enter the information. Okay. So this is a rather simple example of how machine learning works in essence. In actual application at NVIDIA, we actually have many applications of machine learning. Here I show on the left-hand side an imaging mechanism to look at the lunch you have and figure out how much money that you need to pay for your lunch. And it's quite interesting in a way, because I always eat salad, and I put the salad there, it recognizes the salad. Okay, it's $4. Great, so I just pay $4. On the right-hand side, this is an internal tool that we made to suggest the circuit specifications. So what we had before is that we had this problem of incorrect specifications in the data sheet. And since data sheet is the source of all the information, if you have an error in there, how would you know? No one knows except the designer. But however, there are so many specifications, designer cannot be so careful with hundreds of specifications. So what we did is that we look at all the previous specifications, and we created a prediction mechanism. In this particular example, minimum spacing. The designer in this particular cell put down this number, and the suggestion is, well, 80% of the time it was 0, but in these other things these other numbers. So the designer has a way to look at the previous history of what that entry should be, and he can make a decision on what it needs to be. And it helps to narrow down the error rate of the specs. So that's a pretty successful application of machine learning using prediction from the previous data. Another example is this mechanism from Solido. They have this statistical PVT mechanism that will cover 4 sigma with only 300 simulations. So this is also another machine learning mechanism. It creates a model, it makes a prediction, and you just need to do iteration of simulation to see if that prediction is accurate. It learns slowly or maybe quickly, not slowly, that's a bad word. And at the end, you gain efficiency out of that. Now the question is, is the machine just going to learn and replace all our jobs? Well, perhaps. Today, the learning mechanism is actually doing pretty simple functions like predicting models, predicting specs. But can it create things? Well, that's a $1 million question, because we as human beings pride ourselves to be creative, so to speak. So lo and behold, this team from the university created this picture, and all it did is that it made the machine to look at master level paintings and said, hey, create this picture from the essence of this painting. And this is the result on the right-hand side. So I don't know about you. I think that's pretty creative. So it means that the machine learning technique actually is pretty powerful, and we are only seeing the tip of the iceberg. So what needs to happen for the EDA industry is stop just providing us with data data is nice, but we really want decisions. And so all you need to do is put a layer in the machine, in between the data and the decision, and it will actually give us, the machine algorithm will learn about what the decision should be by looking at the data. And EDA industry is in a perfect position to do this type of work. So that concludes my really brief introduction about machine learning. Thank you.
Any digital block that has n inputs, so I need to do some power analysis on it, and also use that data to subsequently do the IR analysis. The problem I have is basically, given that n input, I may have 2 raised to the power n combinations of vectors. So the problem is very similar to either Monte Carlo or fast PVT approaches. You pick either one. The main problem is number of samples is very, very large. And in some cases, the actual simulation time can be very long, even with one vector, because it can be a fully extracted netlist and so on. So out of that many massive, like 1 billion samples, can machine learning be used to do, basically come up with a smaller set of vectors that can not only be used for power analysis, so that we don't end up using this vector-less approach or activity propagation approach, which is mostly pessimistic. So I haven't seen any paper or publication on doing vectorless power analysis or IR analysis using machine learning.
So you are describing a problem that is a classic need for this notion called principal component analysis. So what you do is that you somehow vectorize your problem, and a vector could have nth dimension, but you have no idea which dimension is the most important one. And what you do is that you use a clustering mechanism to figure out what is the principal component of the problem. And in that, you will realize that, oh, your problem only has, even though I have 100 variables, it's really only 5 of them that's really important. And you run through that into the regression of the principal component analysis, and you can reduce your design space. And that's usually the classical way of how to reduce that problem.